Now we will discuss about the solidification of alloys. And as you all know that an alloy freezes over a temperature range rather than at a single temperature. And the exact range of solidification depends upon the alloy composition. So as you can see from this figure, that this is the pouring temperature and the heat is extracted from the mold and it starts the liquid cooling, and at a particular temperature the solidification starts. And unlike in the pure metal, it was occurring at a constant temperature. That means the freezing was initiated at a particular temperature, and at the same temperature it was completing. But however, in this case, you can see there is a decline of the temperature, and then after this freezing is completed, the solid is cooled down and it is brought to the room temperature. So this particular behavior is also plotted on a phase diagram. Basically, it's a binary phase diagram, and this alloy consists of two elements, nickel and copper. So as you can see that pure nickel, it solidifies at this particular temperature, 1455 degrees centigrade, and the pure copper solidifies at 1083 degrees centigrade. And then if you see that, if you consider a mixture of these two elements, so you will have this type of solidification behavior. It will be observed in the phase diagram. And this upper line shows the liquidus line, and this bottom line shows the solidus line. So as the temperature drops, freezing begins at a temperature. It is denoted by the liquidus, and when it is completed, it reaches this line. It is known as the solidus. And the range, temperature range for a particular composition, this range is the solidification temperature range, and sometimes this region in the casting is known as the mushy zone. So we'll discuss that what is a mushy zone. And so the solidification of alloy initiates like pure metal initially, and there is a formation of thin skin. It's formed on the mold wall surface, which consists of fine grains, and it is happening due to the liquid metal faces a large undercooling, and at this point the nucleation rate is maximum. So due to this, fine grains are formed, and this is all happening due to a large temperature gradient at the mold wall surface. So as the solidification process initiates progress, there is a grain growth, and the formation of you can see the grain growth takes place perpendicular to the mold wall surface. And as you can see, as you already know, that we have already discussed in the welding solidification of the welded components. So in the alloy system, these grain growth takes place in the form of dendrites, and it is happening due to the rejection of solutes into the liquid portion, and the solidified portion, it acquires the dendritic shape. And between these dendrites, basically your liquid metal is trapped, and this can say this particular region of solid and liquid, where the solid and liquid region coexist, this particular region is known as the mushy zone. It's a mushy zone, means this is a semi-solid type of consistency. It is having a soft consistency, and the solid region or the dendrites are kept on rejecting the solutes in the liquid region, and it is happening because with the decrease in the temperature, the solubility of the solute is decreased, and this rejection into the liquid metal, this of elements, is known as the segregation. And due to this, another type of cooling was observed that we have already discussed. It is known as the constitutional supercooling. So basically, there is it's a gradient of the composition from the solid phase to the liquid phase. And due to this, large number of solute is getting rejected into the liquid and forming the segregation. And at the center of the casting, so if you see, this is the diagram which shows the solidification of the alloy in the mold cavity, and initially the thin skin is formed all over this mold surface, and it consists of fine grains as the nucleation rate is very high, and the heat is it is extracted from the mold surface into the surrounding, and then due to this decrease in temperature, nucleation stops, and you can say there is a grain growth, and this solidification is progressed. And this grain, if you see closely into the microscope, these are of dendritic in shape, and these are rejecting the solute, these elements into the liquid metal, and then at the center you will form this segregation of elements, and at the center the heat transfer rate is low as compared to this mold wall the mold wall surface. However, the undercooling is still there, which is enough to cause the random nucleation, and as due to the presence of these segregation of the elements, it results in the equiax dendritic microstructure. So if you remember the curve between the G and R, that means the heat transfer rate and the solidification rate. So if the heat transfer rate is less and the solidification rate is high, so you will get equiax dendritic microstructure. So this type of microstructure is observed in case of alloy, solidification of alloy. And now in casting, we always take care of the directional solidification. So what is directional solidification? In casting, we always aim to minimize the different types of defects, damaging defects, which are arising due to the shrinkage of the casting. And the region of the casting which is most distant from the liquid metal supply, which means that the position of the riser should freeze first. So means your riser should freeze or solidify in the last, because if it is not happening, then you will not have any enough liquid metal, molten metal, to compensate the solidification shrinkage. So if this is happen, if it is happening like that, riser is not solidifying, but the casting is solidifying continuously. So in this way, the molten metal will continually be available from the riser to prevent the shrinkage voids during the freezing. And this type of solidification means in a particular direction, means from the casting to the riser. This type of solidification is known as the directional solidification. And as you all know that the surface area of the mold cavity or the casting, it affects the heat transfer rate. So it means that more is the surface area, more amount of heat, or faster in the faster rate the heat is extracted from the cavity, and the casting will experience more cooling, and it will have lower solidification time. And to ensure the solidification of the casting before the riser, the surface area of the casting should be more than the surface area of the riser. Another important factor which comes into picture here is the volume of the casting, and it is related to the total heat contents in the molten metal present in the cavity. So the ratio of this surface area and volume of the casting, surface area of the casting to the volume of the casting, this is equal to the cooling characteristic of the casting. And this particular ratio of surface area to the volume, if it is more than the surface area of the riser to the volume of the riser, then you will have this particular condition that your riser will solidify in the last as compared to the casting. So so the ratio of surface area to the volume is often used to define the cooling characteristic. And higher is this value of this SYV, then high amount of heat will be transferred away from the casting zone. And if this surface area of casting to the volume of the casting, if this particular thing is greater than the value of the riser, then the casting will solidify much earlier than the riser, and the metal in the riser will remain in the liquid state for the longer time duration, and this will help in compensating the solidification shrinkage. So these are some of the rules that we always remember in our mind while designing the riser. So somewhere I told you that it is very important to design the riser, because if it is not carefully designed, then definitely you will have these types of shrinkage, solidification shrinkage defects. It will be observed in the casting. So Here you can see this is a very general diagram. You will have this pouring cup, and then you pour it into this sprue, and from there the liquid metal reaches into the mold cavity, and whatever be the extra amount of liquid metal, it will be filled inside the riser. So during the solidification of the casting, some of these the volume shrinkage will occur, and it will have some shrinkage defect. So in order to compensate this shrinkage defect, the riser must supply the molten metal into this die cavity, and at the end it should be the place which should solidify in the last. And in order to promote this directional solidification, the foundry person, they use some you can say arrangements which are known as chills. So as the name suggests, that chills are the arrangement which are used to cause the chilling effect, and these are internal, or sometimes these are used as external heat sinks that causes rapid freezing in certain region of the casting. So as the name suggests, chill, so it provides the chilling effect, and it serves as a heat sink. So you all know that heat sink, what's the role of a heat sink? Heat sink is used to increase the heat transfer rate, and it is used to promote the rapid freezing in the casting. Then these are of two types. One is the internal chills and other is the external chills. So as you can see from this diagram, that this is the mold cavity, and then you have placed a chill, internal chill. So what is an internal chill? So these internal chills are small metal parts which are placed inside the cavity, and before it is placed before the pouring of the liquid metal, so that the molten metal will solidify first around these parts, and the solidification initiates from the center of this portion. And but the thing is that you should have a chemical composition similar to the metal being poured. So internal chills should have a chemical composition similar to the metal being poured. Otherwise, it will cause an inhomogeneity in the casting, and it will cause a defect, or it will lower the performance of lower the strength and other properties of your cast product. And now there are external chills. Suppose if you don't want to add an extra material into the casting, so sometimes the external chills are also placed. These are the metal inserts placed in the wall of a mold cavity that can remove the heat from the molten metal more rapidly than the surrounding sand in order to promote the solidification. So you all know that sand is a ceramic material, and it has a lower heat transfer that rate. So in order to improve this heat transfer, you can attach metal chills, external chills, in order to promote the solidification process. So now the solidification will initiate from this region, and then it will progress toward this side. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.